Alright, now I'd like to talk to you about standard deviation, which is a brilliant way of describing how widely distributed the different measurements in a sample are. But we have to assume that the sample has a normal distribution. So here we're going to talk about a standard deviation of a sample. We're going to talk about standard deviations of a whole population next week. That's slightly different. Here we're talking about a sample that's taken from a whole population, a larger population. And so standard deviation is represented by the letter sigma. That's a small sigma. And sigma is equal to the square root of the variance. And what's the variance? So variance is represented by sigma squared, and that is equal to the sum of x minus the mean squared all over n minus 1. It's n minus 1 because it's just a sample, not a whole population. Okay, so what do all these different things mean? So what we're doing here is making a sum of, so this is looking at the distances of individual measurements from the mean. Okay, and then we're kind of take an average of those distances, and the reason it's squared is so that because it could be in either direction, so that's so that all the distances have the same sign. So that means if you've got a measurement that's above the mean and a measurement that's below the mean, they're not going to cancel each other out. So an alternative might have been to say the absolute value of each of those numbers, but we're using the square. Okay, so that's what the variance is. The variance is kind of an average of the distances of all the different measurements. I say average because we've got the sum of all these, and then we're dividing it by the number of measurements, minus 1 because it's a sample, but same basic idea. So that's the variance, and then we take the square root of that, and that gives us the standard deviation. Alright, so shall we take an example? So how about we've got a sample, so let's say we've got 1, 5, 8, 10, 16, 20 millimeters. And so n is equal to 6. We've got 1, 2, 3, 4, 5, 6 different measurements. And the mean is, we add those all up, we get 60 divided by 6. So that's 10 millimeters. Alright, so now let's work out the standard deviation. First of all, I'm going to work out the variance. So that is equal to the sum of x minus squared all over n minus 1. So in this case, that means we're going to have to do a sum like this 6 different times. So we're going to take this first one, 1 minus the mean, which is 10, square it, then add it to, same thing for 5, so that's 5 minus 10 squared, plus 8 minus 10 squared, plus 16 minus 10 squared, plus 20 minus 10 squared. And that whole thing we're going to divide by n minus 1, which is 5. Okay, so that's how I'm putting into action this formula here. So that means, I'm just going to work through this. That means this is minus 9 squared, plus minus 5 squared, plus minus 2 squared, plus 6. Oh, I've forgotten. Uh, 10 minus 10 squared. Excuse me. Plus 10 squared plus 0 squared. Not that it would have made much difference. And so that's 81 plus 25 plus 4 plus 36 plus 100 plus 0, all divided by 5, which comes to 246 over 5, which is 49.2 millimeters squared. So that's our variance, sigma squared. And now we want to work out the standard deviation. So that is just the square root of 49.2 millimeters squared, which comes to about 7 millimeters. So we know from, if we draw out our bell curve, like, that's pretty ugly, let's try again. Not much better, sorry. So we've got, here's our standard deviation curve, and so here's our mean in the middle, that's 10, and we know that we've got the same shape for the curve, so we know that 68.5% of the measurements are going to be within one standard deviation of the mean, i.e. between 10 minus 7, which is 3 millimeters, and 10 plus 7, which is 17 millimeters, and so on. Okay, so this gives us an idea of the distribution of the different measurements around the mean in our sample.